How does this idea of locality make our life much easier? We have seen that in terms of different memory technologies, we have some fast storage technologies, but they cost more per byte and actually have less capacity and actually require more power and heat. Okay, and we've seen that the gap between CPU and the main memory is widening. And so if you write our basically well-written programs, if you write the programs well, then they tend to exhibit good locality. And with this, then we can actually have a computer that is both fast and provides large memory space. Okay, and this means that we will have an approach which is called a memory hierarchy, which I have discussed here. Now, what do we mean by a memory hierarchy? What it means is we will have different levels of memory elements implemented with different technologies here. Okay, we have at level 0, we are talking about registers. Okay, at level 1, we are talking about level 1 cache, which is implemented as an SRAM. And then I'll tell you what a cache is, by the way. And level 2, again, again with SRAM technology. And level 3, I have main memory, which is implemented with DRAM. Level 4, I have a local disk. Okay, and level 5 can be, web servers, something over the net. Now, when we go up here, when we go in the upper direction, the amount that you can provide, like the memory element, it gets smaller. Like think about how many registers that we have here. We are not talking about megabytes or gigabytes or even kilobytes, but they are like in terms of like bytes. We are talking about 64 bytes here and etc. But they are faster because they are right on the chip, and they are costlier because of the technology that they have. And then they're costlier per byte, and so that's why we have so few of them. And when we go down here, then they tend to become larger, okay? But they also tend to become slower. So if you go down, then the technology will become slower, larger, but also cheaper per byte. So when I'm buying a disk, you're not talking about kilobytes. You're not talking about megabytes. You're talking about terabytes nowadays, right? And in terms of main memory, you're not talking about bytes or kilobytes or almost on gigabytes. But when you go up here, then you have like this. So basically, like we have the registers at the top, where we have our CPU registers hold words, where we do. And then L1 cache, basically what you try to do is each of the upper elements here, okay, they have less space, so they just copy the most used items, okay, here, okay, in the upper layer. And with this, what I can do is like think about registers, right? In the case of a register, I just bring in, and this allocation is done by the compiler. Okay, you just bring in you store the variables that are accessed. The variables that are accessed is actually are brought into the register. So now let's discuss about caches. What's a cache? I'm sure you have heard about what a cache is. Basically, as a noun, a cache is a smaller and faster storage device that acts as a staging area for a subset of the data in a large, slower device. And what we mean is, in the case of, if we look back here, we have the main memory here, right? And then we have the CPU that's working here. And then in between, we have these caches, sometimes L1, L2, sometimes we have L3 caches. I'm not sure, I haven't heard about L4. But these caches, they are faster memory elements. So you just bring in the memory, the data that you are using to the upper layer here, so that the CPU can access them much faster. And typically, just to give you an idea, if your data is in the registers, for example, you can access it with within 0 cycles. Okay, meaning that it's immediately available. If you're looking for example, say L1 cache, then you can get your data in say 4 cycles. So you do it. And if you're looking for example, L2, we're talking about at 10 cycles. Okay, so if your data is in L2, and if you're talking about your main memory, it can be up to 100 cycles. So that's basically, as a result, you want to bring in the data and instructions that are likely to be used through these upper layers. You make a copy of them essentially, and then such that you can then you have a fast, basically, access to data. And what we call here as cache is that it's this like we have this cache, which is noun. Okay, a cache is something that's resides with this, like with the CPU, okay, processor, and then we have this main memory, and in between then we have these different memory elements, like this. We call this like the one that's closed, we call this level 1 cache. Okay, and then you can have level 2 cache, okay, and then level 3, and etc. Up to, so all these middle layer, okay, memory elements that are in between the main memory and the CPU, we call them as a cache. Okay, cache memory. It's smaller, but it's faster and closer to CPU. And then we also use caching as a verb. And caching as a verb is basically the idea that, when we talk about, multiple layers, and you have seen the layers, then we say that, if I have these 2 layers, then there's caching here. Caching takes place, okay? And in this case here, caching and cache are a little bit as such. And you can see that, for example, as we will see here, there's caching between L1 cache and register. There is caching between L2 and L1. There's caching here. And like when we talk about disks, okay, actually we will see that main memory is a cache for your secondaries, for your disks, okay? And now, when you use the cloud, and the cloud, your main disk is actually acting as a cache for the cloud, for example. Okay? So there's caching between all these different layers. And we say that this is a memory hierarchy, and the idea is for each k, like we have k and k plus 1, for example, the faster and smaller device at level k serves as a cache for the larger, slower device at level k plus 1. Okay? And we will make this is a memory hierarchy. It works because of locality, because programs tend to access data at level k more often than they access the level at k plus 1. And thus, although storage at k plus 1 is slower, but larger and cheaper, and so that's how we can do this. So the big idea is that we have the memory hierarchy creates a large pool of storage that costs as much as the cheap storage at the bottom, but that serves data near at the rate of the fast storage at the top.